So I guess then we can get started. So welcome everybody back to the One World Probability Seminar. It's a great pleasure to have Günter Last from Karlsruhe and Moritz Otto from University of Leiden here today, who are going to speak about disagreement coupling of Gibbs processes. So Günter, stage is yours.
Okay, so first of all, thanks for having invited me. It's a wonderful tradition, I have to say. And before, while preparing the talk, I've checked a little bit the list of former speakers, so very, very interesting. I'm going to talk about some work I have done a number of years ago. Together with Moritz Otto, who is the second speaker today, and then later with Steffen Beetsch. But the thing is still very, I hope so, very interesting, and it's a technique which can be used in order to establish asymptotic results for Gibbs processes, that is, for processes with misdependencies. Okay, so here is the setting. I'm somehow have the my task is somehow to introduce the concept and to prepare the stage for Moritz's application. Maybe I will have one or two applications as well. So we are starting in an abstract setting. I'm sorry, I have to apologize because I can't draw pictures. I cannot write. So this is due to some. Yeah, I'm a guest here in Berlin at the moment, and I'm not in my usual working environment. Okay, so we are working on a Polish space. Could be RD, could be a space of particles, could be a space of functions, and we are looking at point processes on this phase space. And in order to do so, we introduce the set N of all locally finite counting measures. So that's quite standard. So a point process is then a random element in this N, and if you like, you can think of this point process as of a locally finite random configuration, at least if you don't have multiple points. The restriction of a measure is denoted by a subindex, and of course the most famous point process is the Poisson process. You see this in item 5. And the Poisson process has just one parameter, which is the intensity measure. And the notation for this Poisson process distribution is pi nu. Okay, so that's notation. And now let's talk about Gibbs processes. So there are several ways of introducing a Gibbs process, and the most elegant way is due to some remarkable and wonderful paper written by Guyen and Cécine. I will have some references at the end of the talk, who realized that the usual description of a Gibbs process in terms of local conditional distributions can be somehow summarized in just one equation involving functions f of two arguments. The first one, x, comes from the state space, and the second one is, in this case, a point process. So on the left-hand side, you see the expected value of the integral of f on x psi dx. Remember, psi is interpreted here as a measure. It's a random element in the space of measures. On the right-hand side, you see again an expectation and then the same function x. But now you replace this point process, you are adding to the point process some extra additional point x. This is now measure theory notation. Delta x is the Dirac measure in x. So in terms of the point process, this just means add a point x. And this comes with a certain weight, which is the famous Papangelo intensity kappa. And this kappa is a function, as you can see in the first line on this transparency, of the state space X and configurations, or locally finite counting measures. So that's a very dry definition of a Gibbs process, because here we are, what's going on, where's the interaction, where are conditional probability distributions and things like that. Let me comment that if the kappa is equal to 1, which means somehow no interactions, then you get the famous Mecke equation, which is characteristic of the Poisson process with intensity measure lambda. So somehow the kappa expresses the interaction between X and the configuration psi. Okay, so what's the what can we do with this equation? And I will tell you a little bit more about condition distributions later. The first thing we can do is to iterate this kappa in the way you can see this in this definition. So using this kappa, this Papangelo intensity kernel, there's a historic reason for calling this like that. We can iterate this thing. So we can first take x1 and look at the kappa. Then we have added the point x1, which resides in psi plus delta x1, and we look at the second point and so on. And then if you iterate this Guyen-Cecine-Georgi equation, G and Z equation, then you end up with the formula in this theorem, where you now, instead of integrating with respect to psi, you are integrating with respect to the so-called factorial measure of psi. And that's the following thing. Assume psi is sitting in a countable number of points, and then the psi m is just summation over m tuples of these points with different entries. Yeah, so excluding the diagonal. And then you get somehow the same formula, but now the kappa is replaced by kappa n, and instead of adding 1 point x1, you are adding points xm. And that's very, very important equation, even if kappa is equal to 1. Then it's called multivariate Mecke equation. And it's really hard to find any paper on stochastic geometry based on Poisson processes which is not using the multivariate Mecke equation. It's just very, very hard because it comes so natural. You think, you know, these points of psi, they could form a graph, for instance, where the edges are somehow, Peter, you know, so you're very familiar with the random connection model. So you have all these edges, and then you are interested in geometric objects, in edges, triangles, and so on. So what triangles? I have to take 3 points. And so it's very, very natural to look at functionals which occur on the left-hand side. And this equation is very, very fundamental, even for the Poisson process. But now we have it for the Gibbs process. Okay, next, transparency. And by the way, if you take now the expectation of this kappa m, then you get another famous object in point process theory, which is the m's correlation function of psi. And as I learned from physicists describe a point process not in terms of distributions on n or something. They think of correlation functions. These are very crucial objects, in particular in the case m equal to 1 and m equal to 2, in which case they decrease densities and correlations. But now, for those of you who are familiar or you have seen Gibbs processes in the statistical physics literature, here is a way to rewrite the G and Z equations in an equivalent way called Topruschin-Lanford-Rouelle equations, DLR. In order to do so, we introduce an Hamiltonian, which is a function of 2 arguments, and both arguments n, so they are locally finite counting measures. You see the definition there. Then we define what is called the partition function, and we can as the integral of e to the minus h with respect, now you might have forgotten my notation, p lambda b. That's the distribution of the of a Poisson process with intensity measure lambda restricted to b. Or equivalently, you take a Poisson process in the whole space and restrict it to b. That's equivalent. And this h function is really called, you can actually think of h as of an energy. So what is the energy of a configuration psi given somehow the mu as a boundary condition? And then the set b, what you see there is the famous partition function, maybe up to a constant. Okay, and now it's getting a bit more, now talking about conditional distributions. So if you start with this G and Z equation as the defining property of a Poisson process, then this partition function, if you plug in the restriction of the point process to the complement of a bounded Z, then the partition function is finite with probability 1. It's actually almost positive because by definition, if I go back, because the Poisson process has a non-zero probability of putting no points in a bounded set. E to the minus something finite is positive, and then the h is 0. E to the minus 0 is 1, so there is the partition function is always positive. But it's finite if I plug in a boundary condition, any boundary condition. And then you see the famous DLR equations, Dobrushin-Lanford-Ruel equations, telling you what's the conditional distribution of the restriction of the Gibbs process to a set B, given what is happening in the complement. And it's absolutely continuous with respect to the Poisson distribution, and the density is e to the minus energy. So the higher the energy, the smaller the probability. And the factor, the partition function, of course, is just a normalizing. 1 minus the partition function is just the right appropriate normalization. And quite often you see in the literature this as a starting point. So people are defining Gibbs process this way, and then we can be happy to have this integral equation, which is not local. So the nice thing of the G and Z equation is there's no B. Yeah? Here you have a whole family of conditional distributions, but in the integral characterization, you have just an arbitrary measurable function of 2 arguments. Okay, I think I have 45 minutes. So I will go through the second chapter section briefly, but I will mention it. Because this is still not the way Gibbs processes are defined in statistical physics. What's the way? People start with interactions, pair interactions, triple interactions, multi-body interaction things. They are starting with interactions. They are forming a Hamiltonian, an energy function, and then they define the Gibbs process locally in the way we have seen it, but in the DLR equation. But in order to do so, you have to somehow to describe the interactions. So maybe just in words, maybe the most one of the most famous models in continuum is the hard sphere model. So you have balls in space, and you just forbid intersections. So the interaction is, so to speak, infinity if 2 balls overlap, and it's 0 otherwise. This is also sometimes called hard spheres in equilibrium. That's a purely pairwise interaction, which is extremely strong, and it's overlapping is forbidden. Otherwise there's no interaction. In a sense, this is a Poisson process in bounded window under the condition that there are no overlaps. And already for this simple process, mathematician cannot prove that many things. In particular, we haven't proved phase transition rigorously. We could only prove that there's a unique Gibbs distribution if the activity, there's a certain activity parameter is small. So that's an example, famous example of a pair interaction. You can generalize this to soft balls, so to speak, where you allow somehow that the balls can penetrate each other. Anyway, I will maybe go through this rather quickly. So the general picture is again from this wonderful Nguyen-Cecine paper. You take any function on finite configurations, that's my symbol in less than infinity, finite configurations, finite counting measures on the state space. Then you can build energy functions. So I go through this quickly. And then you can define the partition function now in the way we have seen it before, but now starting with the interaction. So starting with the interaction, we define the partition function, this famous partition function, and we say that a point process psi is a Gibbs process with this potential, with this interaction potential, if you just have the DLR equation. And now we have two possible ways to define a Gibbs process. Namely via the DLR equations and via this Papankilo intensity kernel thing. And voila, read the classical papers. I can only recommend this, going back to the classical sources. Such a wonderful paper. It's equivalent. So a Gibbs process can either be described starting with the interaction potential, and then we have this integral equation and the other way around. In this example, you see again the case of a pair potential, which is just a function on finite configuration, which is zero unless C, the configuration has 2 points. So this was a brief introduction into Gibbs processes. Very brief, of course. Are there any questions so far?
Perhaps just, so I think you said it, but you're saying that these two definitions of Gibbs processes are fully equivalent. So you cannot find one in one definition that would not be constructed in the other.
Yeah. Yeah, that's what I'm saying.
Mm-hmm. Thank you.
Yeah. So now let's talk about, let's getting closer to disagreement or agreement coupling. So Poisson thinning. So first of all, the setting. So here we are restricting for a while to the case of a diffuse measure, which then means that the corresponding Poisson process is simple, no multiple points, and to a finite measure. So basically what we are doing now, we are looking at finite configurations. So think of this local description, that's what we are doing. I mean, we are dealing with point processes in a bounded window. Maybe we increase the window then to cover eventually all of RD, and then we are interested in limit theorems. But first of all, we start with a bounded window. So it makes all sense of the world just to focus now on the finite case and to see what we can do. Okay, so we fix a potential Papankilo intensity, which is satisfying this core-cycle condition. That's, by the way, if you start with the NGZ equation, then this is satisfied for almost all x, y, and mu. So it's not a strong assumption. And for technical reasons, we are, as for instance, you might think now that we are on RT, okay? And we would like somehow at the end of the day, we would like to represent a Gibbs process as a thinning of a Poisson process. And some of you might have seen this, maybe even all of you have seen how to generate more complex point processes on the line by thinning a Poisson process on the line. And that's the idea here as well. But on the line, we have a lot of structure. We can order the numbers. But here we are on RD, and we would like to save some of the ideas which are so well known and very useful on the line. We would like to use some of these ideas also in space, and in order to do so, we take some Borel isomorphism between X and a Borel subset. We can do this. Then we say X is less or equal to Y, if phi of X is less or equal to phi of Y, where phi is the isomorphism. And this gives a ordering. So which is a bit implicit because everything depends on phi. But anyway, we can do this. There's a way to order points in a measurable way. So we have kappa, we have the Poisson process P lambda, so we can define also the partition function ZB. The definition, I show you this here. This was the first part. This is the definition. So everything is defined in terms of lambda as lambda B cannot taken as lambda because lambda is finite. Kappa is given, so we can define the partition function. Okay. Good. And now something mysterious is showing up. So Moritz, you remember when we first did see this, we were struggling, and maybe we are still struggling because that's a definition of a function of x and psi, similar to kappa. But anyway, so we take the kappa. I mean, I can only read it. I can give you some interpretation maybe later. But here we take the kappa and plug in the x, but as a configuration, we take all points smaller than x. And that's not well defined because we have an ordering. So we can restrict the configuration psi to all points strictly smaller than x with respect to this ordering. And then we modify this kappa with the fraction of two partition functions. And the partition function, first of all, the index x infinity, this is the set B, which showed up as everything. We are talking here about partition functions in the set B. And the argument is somehow the boundary condition. But in the numerator, the boundary condition, which is the restriction of the configuration up to point x, is we are adding an extra point x, and in the denominator, we don't do this. Okay, it is, if we assume, and that's what we are doing now, that the kappa, it's the second definition, that the kappa is bounded uniformly in psi, which is a quite common assumption in this business. So we have a bounded Papangelo intensity in the configuration, and alpha could be a constant. If it's not a constant, it should be integrable with respect to the underlying measure lambda. We can call this stability. So that's some sort of stability. So if kappa is smaller than alpha, then it's a matter of calculation to show that this P in the first definition is also smaller than alpha. And the idea is now to select points of a space-time Poisson process according to the probability P divided by alpha. Yeah, if I had here some possibility to draw a picture, I would probably show you the Poisson embedding on the line, which is such a beautiful idea. You know, maybe I try it with words. If you have a Poisson process, if you have some point process on the line, and then you draw a plane and a Poisson process in the plane, just with unit intensity maybe. And some of you know that there's the notion of the stochastic intensity, which is somehow the infinitesimal probability of a point showing up at some time, given the history. And you can draw this curve in the plane. And then you are searching for the first point of this space-time Poisson process, which is falling below this curve. That's your first point. Then you update your intensity because the history is changing. And you get another curve. And then do the same thing. You look for the first point of the time-space Poisson process, which falls below the curve. It's a very beautiful thing. It's Poisson embedding, and it's a very useful thing. And in a sense, we would like to do it as well. And in order to prepare this, here's a preliminary result, which is not using space-time, but just the direct thinning. I mean, okay, let me just explain the ingredients. So what you can see here is the distribution of a point process. I'm integrating with respect to phi, and the phi comes from a Poisson process with intensity measure alpha lambda. Alpha lambda means you need to take the probability, to take the measure which has density alpha with respect to lambda. Alpha might be a constant, okay. Okay, then I'm choosing a configuration psi which is less or equal than phi. In other words, I'm picking some points from phi in a certain way. And the way I do it is just with these probabilities, namely the px psi, which is this mysterious modification of the Papageno intensity kernel, normalized, and 1 minus this, okay? And here's surprisingly, or maybe not surprisingly, it's the distribution of the Gibbs process. That's very nice. There's no time here. I mean, some of you might have seen, I mean, you can simulate a Gibbs process by a Burst and Des process in bounded windows. It's quite well known. It's the invariant distribution of a Gibbs Burst and Des process is suitably chosen according to Papageno intensity. Here's no time, directly in one go. You take a Poisson process and you can sin it in one go. Okay, one might argue that P is not very explicit. Okay, that's true. But Moritz will show you, and maybe even I can show you in the last 5 minutes, it's still useful. Anyway, what is even better is to introduce the time here also, and again to generate the Gibbs process in one go by a generalization of this Poisson embedding. And maybe the details are not that important, so important here, and they are technical. That's true. At some stage, when dealing with Gibbs processes, things are getting technical. It's just something you can't avoid. So here's the setting now. We are now getting back. We have again a diffuse infinite measure on X. Later, we have to make sure that we can how to deal with infinite measures. I can tell you right now, the restriction of the conditional distribution of a Gibbs process is again a Gibbs process. So it has, you just have to modify the Papageno intensity. So we have a potential Papageno intensity kernel kappa, and now we take a Poisson process on space-time, where on the time axis we choose Lebesgue measure, homogeneous in time. And now the goal is to represent the Gibbs process as a function of the space-time process. I mean, in the previous thinning picture, you haven't seen, you know, the thinning decisions have not been made explicitly. There were no random thinning variables. Now we make it more explicit. Okay, maybe I don't. I mean, I have uploaded other files, by the way, they are available for all participants then, so they can access them also later after the talk, or what's the...
Yes, so we will put them on the webpage. I think they're not
available.
Yes.
They will be
Everything.
available. Yeah.
Okay, so you know, maybe that's my excuse now not to explain this. But in principle, I've indicated this already. Namely, I choose the points of my Gibbs process successively. That's the idea. And successively is referring now to the ordering. And I'm really drawing pictures. You know, I do this, I take the sinning probabilities, P, and I take points from realization of the space-time process successively, but only the space coordinate. The time coordinate is used to, you know, to define besser and below or above the curve. Okay, so there's an algorithm which is semi-explicit, semi because, you know, everything is based on this ordering. And if you do it in the right way, voila, then this function t of now this phi, which is the space-time Poisson process, is a Gibbs process. One go, one sinning go. The disadvantage is it's just for finite configuration. So we cannot talk here about infinitely many points. That's not covered by this result. Okay, now disagreement coupling is already an application of this sinning, this Poisson sinning, and here how to go from this global Papangelo intensity to the local picture, where we have this conditional distribution, is actually a very pleasant property of a Papangelo intensity. Namely, if you have a Papangelo intensity, kappa, and you are interested in the conditional distribution, as you can see it here on this transparency, then this conditional distribution is also a Gibbs process. And the Papangelo intensity, basically what you have to do, you have to add to the second component the boundary condition. It's very, very nice thing. So actually, you can transfer the global Papangelo intensity kernel to the local picture just by taking into account the boundary condition as written there. Okay. And now to do disagreement coupling, there's one ingredient more. I'm sorry for this, but it's important. We have to assume that the Papangelo intensity kernel is localizing in a certain sense. So what you can see there in this third bullet is that the kappa x mu the dependence on mu is only via a certain cluster, let's say, or a certain set which is associated with x and mu. And formally, we define this cluster component or whatever via a symmetric relation on x. So that's a further ingredient here. For instance, the underlying space could be the space of particles, and then the similarity relation is then indicating that the two particles intersect, for instance. So somehow this kappa localizes, which is a quite common, as you will see this in Moritz talk as well. It's a quite common assumption. If you are dealing with dependencies, you always, I would claim, always make some sort of local dependence assumption. Yeah, somehow the points which are far away from x shouldn't contribute to this kappa. Okay, so that's a localizing, that's an assumption. And then Vandenberg and Mees in 1994 in a very influential annals papers dealing with discrete processes, then Hofer-Temmel and Rude-Beer in the special case of, I think, balls, and then later Moritz and I, we have proved the following thing. So we have the assumptions as outlined before, and now we take two boundary conditions. I call this boundary conditions in NVWC, which means these are configurations on the complement of our, let's call it W observation window. And now here's the trick. that's a coupling now. And the coupling is established via Poisson thinning and stopping set techniques. So what can you see here? You see here 3 objects. No, sorry, it's getting a bit technical, but it's the price you have to pay. But once you can use it, it's a very powerful method, as Moritz will show, for instance. So if you have, we have 3 objects. All of them are point process in the first instance. The Xi is a Gibbs process with the Papangelo intensity kernel with boundary condition psi. This was the previous page. Psi, you know, this page. The psi is now the psi you can see here. It's somehow the boundary condition. So we are looking at the distribution of the Gibbs process fixing some boundary condition. But there's a second boundary condition, psi prime. So we have 2 Papangelo intensity kernels. Papangelo intensity is according to 2 boundary conditions. And the third object is a Poisson process with the intensity measure you can see there. Okay, that's not no big deal. We can look at 3 objects, but now they are coupled in a certain sense, strong sense. Namely, if you take, that's the third bullet, if you take all points which are not in neither in Xi nor in Xi prime. So Xi and Xi, so the idea is really, I like the term agreement coupling actually. The idea is to get Xi and Xi prime as close to each other as possible. That's the idea, okay, for certain reasons. And those points which are not common to Xi and Xi prime, they can be connected to the boundary conditions. That's the 4th item, connected by the points which are available. And moreover, all points of Xi and Xi prime are contained in the support of eta. So Xi and Xi prime are thinnings, very dependent thinnings of this Poisson process eta, and such that the points which are neither in Xi nor in Xi prime are connected somehow to the boundary conditions. So I just tell you that this can be achieved by Poisson thinning and stopping set techniques. And I have 2 applications here, and I'm using my final 5 minutes just to show you one application which has not been published. Maybe that's why I can present it. And the other, I have another application, you can see it on the web pages, which is on uniqueness. Talked about this earlier somewhere. For instance, in Berlin, I think, during a workshop. So let's talk about decorrelation. So we need a setting, lambda kappa, but now we are not assuming that we are on a bounded phase space. We would like to talk about decorrelation. We need this localization property again of the kappa, and we take a function W, function which maps the reals into the non-negative reals, which goes to 0 if R goes to infinity. Think of R as of a distance parameter. Okay. And then these wonderful colleagues, Bartik Blashishin, Yogesh, and Joe Jukic, published back in 2019 a very nice paper dealing with central limit theorems and also law of large numbers for dependent processes, dependent point processes. And the fundamental technique they are using are correlation functions. And they came up with a natural mixing property. You might also call it mixing property, and they call it V decorrelation, W decorrelation, which W is this function. And the idea is not so difficult once you have an interpretation of these correlation functions. So look at the left-hand side of this inequality. You see a difference. So the first term is the correlation between x1 up to xk plus mk and m some integers. And by the way, you can interpret this number. That's why physicists love this notion. It's an infinitesimal probability, namely the infinitesimal probability of having k plus m points at the locations x1 up to xk plus m. It's a very clear interpretation. And now you compare this, or there should be absolute values, I think. Okay, absolute values among this the difference. Okay, and you compare it with the product of the correlation of the first k point and the correlation of the remaining m points. And somehow, if this is going to 0, if you are moving these point clouds x1 up to xk and xk plus 1 up to k plus m away, then this is a sort of mixing. And you see this here. On the right-hand side, you have constants, you have this function w, and you apply the function w to the distance between these 2 point clouds. If this is true, then BYY paper is calling this W decorrelation, which is a very nice property to have. And here we go in a paper with Victor Benesch, is one of his PhD students, Steffen. We proved that we have W decorrelation. I think that's a bit brief here. Well, Becher and Last. Becher and Last are the general. This is the general case. With Victor, we proved a special case of this. So look at this. Here now, that's the first time you see percolation. So far, no percolation. Now we have a percolation assumption, or actually the absence of percolation. So you have this relation, tilde, which somehow defines a graph on the points of a Poisson process. In this case, E alpha lambda is a distribution of a Poisson process, and U comes from this Poisson process. And now you're asking yourself, is 0 connected to the complement of, let's say, a big ball? R is big. If this is smaller than W of R, actually still no percolation in a sense. Yeah. Then the process Xi is decorrelating. But of course, we are interested in the case where W of R goes to 0, not only goes to 0, but goes to 0 sufficiently fast. That's also possible. You can see it also in new results on continuum percolation, where you can see this is actually exponentially decaying. In a Boolean model with bounded grains, this probability is exponentially decaying. Thanks to the disagreement coupling, and now you could call it disagreement percolation. Thanks to this result, you can prove that the process really decorrelates, which is a nice property to have, as shown by BYY. So you have central limit theorems for certain stabilizing functionals. And another thing you can do is you can show with quite some efforts that there's exactly one Gibbs distribution with Papankelo kernel kappa once you are in this subcategory regime. That's joint work with Steffen. It's actually on the next transparencies. There's more. Okay. We can also prove bounds for the beta mixing coefficients, not published, but we need to write this up now. I skipped this. Here's an example, the final example of my talks, maybe this one. So let's assume the space X is the space of all non-empty compact subsets of a Polish space. We like such a setting in stochastic geometry. So a Poisson process on this space is then called the Poisson particle process. Let's say K is this similarity relation is just defined as you can see it. K and L should, I think it should, maybe it should non-equal to the empty set. I'm not sure about that. Anyway, if you non-equal to empty set, I think. So, and if you have now a Gibbs process of particles with a Papangelo intensity kernel kappa, which is bounded and localizes, there are many examples. And if the particles are deterministically bounded, then this Gibbs process is both decorrelating and beta mixing. But I should stop here. Here's a list of references. So the second reference is very, very beautiful paper, very fundamental. Vandenberg mass disagreement percolation. What else? Yeah, in my book with Matthew, there you find the correlation function, things like that. We are thinking about adding a chapter on Gibbs, but we have not decided yet. And here, Günter Last, integral and differential characterizations of the Gibbs process. Wonderful. So thank you very much for your attention.
Oh, so thank you, Günter, for a really nice talk. So are there any questions? So please feel free to unmute yourself or raise your hand. Oh, yeah, Peter, I guess.
Yeah, I'm going to start if no one else will. Can I just ask, earlier when you were talking about I think you referred to it as the space-time Poisson process, right?
Space-time.
Is that a sort of similar idea, of course, more complicated than the idea that of soft local times, because they also sort of embed they limit themselves to embedding a Poisson process into a larger dimensional Poisson process, and then use density functions to essentially thin it out to get sort of various couplings. That kind of sounded like a similar procedure where you said that you're sort of looking for the first point that's below a curve.
Have you mentioned local time? No, that was a
soft local times by Teixeira and who was the other author? Sergei Popov, Augusto Teixeira and Sergei Popov.
And I would need to look it up.
Because the idea there sounded very similar.
If it is related to local time, then that's a different idea. Local time description motion, you can do this. This is in terms of a Poisson process on, so to speak, on time times excursion set.
Mm-hmm.
And then you have to use the inverse of the local time. That's true. That's a beautiful description of the Brownian motion, if you like, going back to Ito and Paulini. But that's not what you mean. So I would need to look up this paper. What the similarity is really, you have. Once again, you have a point process, and I don't know whether the colleagues are doing this, but you are interested in simulating a point process on the line.
Yeah.
And because you're on the line, you can start with the first point, T1, T2, the second point, T3, and so on. And you do this successively. And what you can do, thinning and embedding is, by the way, somehow thinning is more specific than embedding, because thinning, if this curve is bounded, then you can just plug your Poisson process into a strip. You don't need the full plane, because the curve is below some bounded constant anyway. You just need the strip, and then it boils down to thinning. Actually, just and the trick is just to take the right thinning probabilities. And the right thinning probabilities are, and that's pretty much, if you have the interpretation of a stochastic intensity, it's pretty much obvious. It's just the suitable normalized infinitesimal probability of having a point and normalized dividing by the upper bound. But you have to update. Whenever you have a point, you have to update your history.
So, but when you say update the history, is that equivalent to potentially just reshaping the remaining space?
No, you don't need to reshape. Thank you for the question. Maybe coupling, how are we achieving this coupling? We really have one Poisson process. Everything is represented in terms of this space-time process. So which makes the coupling. Everything is a function of just this process. We don't need to change this randomness. But what we do need to change is the curve. Because it changes, if you start with the stochastic intensity at time 0, you have a certain curve, but you have to update it. You cannot take the same curve, the same functions forever. The only case you can take the same curve is the case of a Poisson process, where you don't have any dependence on the history. But once again, I don't know really what this paper you have mentioned is doing.
No, so in the other paper, they are limiting themselves to Poisson processes, and essentially what they're doing is they're sort of stacking the densities on top of each other, sort of additively, and until they reach the next point.
There might be some relationship. Maybe you can be so kind and send me the reference later.
I mean, I can
check it, and I will get back to you telling you what are the similarities and what are the differences.
Thank you.
All right, so more questions? So feel free to unmute. Okay, otherwise, I might have also one for you. So everything you talked in terms of the coupling, you really refer to like an exact coupling, right? So somehow you really map one process like to the other in a certain sense. Could there be like an approximate version where somehow as soon as you go away from the GIPS setup and have maybe some slight modifications, you could still somehow talk about coupling two processes, but perhaps not in an exact way, but like in some sense in an approximate way? Is there anything which makes sense in this direction?
This would the question is, what would you like to do with this? Okay. So first of all, I think it would be good to control the error, the approximation error, maybe. And maybe that's a point, that's a possible direction to do. Maybe you take the wrong kappa, so to speak, but you can still express. You can control the distance, and this is in the spirit of results Moritz is going to present. So you have somehow two maybe GIPS processes, and you are talking about distances between them. They are computing this, bounding the distance. But for our purposes, this disagreement, this decorrelation property and uniqueness of GIPS, it has to be exact. We really need to know that the procedure is producing the correct distribution. Otherwise, I wouldn't know how to use it. But I will not exclude the possibility of making something more general.
No, thanks. Okay, so any more questions, comments? So doesn't seem the case. So thanks, Günter, again for a really nice talk. And I guess we have like maybe a 2-minute, 3-minute technical break.
And I press here stop share, yes?
You can, but I've made all of you co-hosts, so Moritz can just take over if he wants and start sharing.
Yeah.
Which he seems to have succeeded.
Looks very good.
Yeah, I use the break to make myself a coffee. Be back in a second.
Yeah. Yeah, looks very good. So So Moritz, you're still muted and
Okay, sorry.
Yeah.
Yes, but you can
Yep.
see my screen, right? So
Yep, looks very
perfect.
good. Yeah, I guess so typically I would suggest we just wait maybe until Peter's back with the coffee. Then
Yes.
that's a good way. So also just to make sure, yeah, could you so going back and forth works also in full screen, right?
Let me check.
Yeah. Yes, looks good.
Yes, great.
Perfect.
Yeah. Okay.
And I guess also we will cut the video then afterwards slightly.
Yeah.
So successful coffee. That looks good.
Yep. One needs it.
Yeah.
Isn't it like a running joke that mathematicians or maybe physicists are coffee-consuming machines that consume coffee and produce theorems or something like that?
Turning coffee into theorems.
Yeah.
Yes.
Absolutely. Yeah. All right, so let's maybe get started. So it's a great pleasure to have the second talk by Moritz on limit theorems for Gibbs
Yes.
process via disagreement couplings.
Thank you. And I would also, first of all, like to take the opportunity and thank the organizers for giving me the opportunity to speak in this nice seminar, which is really an honor. So in the second part of today's lectures, I'd like to talk about applications about disagreement couplings, and this will be applications for proving limit theorems. And this is actually joint work, first of all, with Günter. I mean, we proved together a Poisson approximation result, and then later with Christian Hirsch and Anne-Marie Svane from Denmark, we went on and looked at normal approximation. Okay, so I would like to start with a brief reminder of the definition of a Gibbs process. So we say that a point process xi with some Papageno intensity kappa is a Gibbs process if it satisfies the G and Z equations, right? And Günther already mentioned that if the Papageno intensity kappa does not depend on xi, so if this is a deterministic function, then this is actually just the Mecke equation, which is characterizing the Poisson process, right? And in this talk, I will assume, and this is a slight simplification to what you heard from Günther, that kappa is uniformly bounded by some alpha, 0, and that it is localized in the center. And the second component, the Papageno intensity kappa, only depends on the restriction to the ball with radius r0, where the parameter r0 is strictly smaller than the critical radius for Poisson Boolean percolation with intensity alpha 0. Right, so Poisson Boolean percolation was the last example in Günther's talk, right, where you have Poisson points and you connect each pair of Poisson points whenever their radius is smaller than 2 times r0. And then so you can study percolation in this model, and there's a critical radius RC depending on the intensity of the Poisson process. And I want to assume now that my parameter R0 is below this threshold. Okay, so this is the two assumptions that I have. And first of all, I'd like to consider Poisson approximation. So what is the setting? I mean, we start to define functionals of a Poisson process. So what we do here is actually that we take a Borel set W, and then we define a point process gamma on this Borel set W as follows. So we take here actually all points x in the Gibbs process xi restricted to W, and then we have a thinning function g, which takes either the value 0 or 1. And this gives us then a thinning of our Gibbs process on the set W. And I assume now that this thinning function or score functional g, that this also localizes in the sense that the decision whether I take a point or not only depends on the restriction of the point process to some set R of x, to some Borel set R. And you see this here in the picture, right? You can think of a certain observation window W, and then if you have a point x here in the left upper corner, then the decision whether you would take the point x or not actually only depends on the Gibbs process xi restricted to this ball, say around x. And the same, of course, also holds for point y that is maybe apart from x. Okay, why is such a functional relevant? I mean, a very classical example is if you, for example, take G to be the indicator that there is no point of the Gibbs process in this ball with a given radius r around x. Right, so what you count then in gamma is actually all points that have at least a certain radius r to its nearest neighbor. And such a choice of G is considered when you, for example, study long edges in nearest neighbor graphs, or also in random matrix applications when you study large gaps, right, in, for example, the Gini-Bré ensemble, then you can also work with similar choices of thinning functions. Okay, so I want to study Poisson approximation in a very strong distance, which is a Kantorowicz-Rubinstein distance, which is defined for two finite point processes, gamma and theta. And this is just the supremum over all Lipschitz functions h, where I consider the difference of the expectation of h of gamma and expectation of h of theta. And I consider here Lipschitz functions with respect actually to the total variation distance of theta and gamma. Okay, and this is a very strong distance in the sense that it actually dominates the total variation distance. Okay, let me give a small embedding of what we do here in the classical literature on Poisson approximation. Günter already said that it's really worth looking at the classical literature, and I think the first two papers that I mentioned here definitely qualify for this. So this is actually a series of two articles by Aratia, Goldstein, and Gordon from 1989 and 1990, where they study Poisson approximation in total variation metric. And what they basically show is that in many applications, the first two moments are sufficient for Poisson approximation. In the second paper of Barber and Brown from 1992, Stein's method was combined with palm theory. And yeah, I will show you on a later slide how this can be understood. Then there are two papers, one by myself and the other one by Bobrovsky, Schulte, and Yogeshwaran, where we studied applications of Poisson approximation in stochastic geometry and came up actually with explicit convergence rates for Poisson input. So in the situation where you don't have a Gibbs process, but just a pure Poisson process, we came up with explicit convergence rates for actually several examples in stochastic geometry. And so in my paper, I looked at the total variation distance, and that was then generalized by Bobrovsky, Schulte, and Yogeshwaran to the Kantorowicz-Rubinstein metric, which is actually stronger, right? And then this is a slightly different line of research. I mean, this is compound Poisson approximation, and it is actually very interesting that it turns out if you were interested in compound Poisson approximation, then it is very natural to study beta mixing input processes in the Wasserstein metric. So the Wasserstein metric, which is a weaker metric than actually even total variation, fits very well to both compound Poisson approximation and beta mixing processes. And there's an early paper by Barber and Monson from 2002, which is an analysis paper, but for some reason, I think not many people have actually read this paper. And yeah, so some years ago, Nicolas Genavier and Christian Robert studied compound Poisson approximation in stochastic geometry. And then last year, and this is still a preprint together with Nicolas, we looked at this again, and basically we combined ideas from Barber and Monson with Nicolas and with Nicolas' work from 2018 and came up with a theory for compound Poisson approximation for beta mixing processes. Okay, so this is a bit of a literature review on Poisson approximation, and I would like to show you now actually our main result in the paper with Günter. Okay, so say you have this stabilization radius Rx, which was actually the stabilization radius for the thinning functional G, which defined our point process gamma, and assume you have a larger set S of X, which contains actually this Rx. Okay. Now I just introduced some notation, so I will denote M, the intensity measure of gamma, and then I take a Poisson process theta with intensity measure L. And the idea is now that I want to compare in Kantorowicz-Rubinstein distance the functional gamma with the Poisson process theta. Okay, and then we have an upper bound, and the first term here is actually just the total variation distance of the two intensity measures. And then you have two terms, T1, T2, and T3. And the first two terms, T1 and T3, they are very classical. So they actually come from first and second moment contributions. So they basically ensure that the first and second moment of gamma converge to the correct terms of theta. So if you look at T1, what you have here, you have a double integral over W, and you take the expectation of your thinning function G times your Papangelo intensity, and then you do the same with X replaced by Y, right? So this is a first moment quantity because you have here the product of two first moments. and you integrate over all pairs xy, which are not too far away from each other, right? So the idea is here that this sets Sx and Sy, they are somehow localized to x and y, in the sense that you should think of this integral here actually of a local integral where you only integrate points y close to x. Okay, the second term T2, this is the second moment term. So here you take the expectation of the product of g of x and g of y, and then you have the iterated Papangelo intensity, which was introduced by Günter. And again, you have here a local integral, right? So Sx and Sy should overlap. So these are very classical terms, and actually you see equivalent or similar terms already in the papers of Aratia, Goldstein, and Gordon, right? And then you have the term T3, and this is actually the term where we use disagreement coupling in order to prove Poisson approximation. And here you integrate over all pairs xy such that Sx and Sy do not overlap, right? So this is an integral which takes care of actually the global contributions. And on the next slide, I would like to give you an interpretation of this probability that Rx is connected via this Boolean model built on the dominating Poisson process eta to this other set here, okay? So this is on the next slide. So what do we have here? I mean, so parts of the picture are actually from the second slide. So you have here a ball around x and a ball around y. And the probability that we consider here now says the following. So you have a path in your Boolean model that connects Rx either to the complement of the whole Minkowski sum of W and S, right? So this is a path that is here in the upper part of the picture, or you have a path that connects Rx to Ry. Okay, and the idea is actually that if Rx and Ry, if they are far apart from each other, then this probability will become small, right? So, and that's how one can show that the term T3 actually becomes small if the sets S and X, if they are chosen in the correct way. Okay, let me go a little more into detail and give you an idea of how disagreement coupling is actually applied here. Okay, so I would start now here with an introduction of Poisson approximation via palm couplings. I really like the theory, and I think it's a very universal theory. And at the moment, we are actually trying to use it to prove Poisson approximation for large gaps of Gini processes, and it has been proven useful in many settings. So what is it all about? So let gamma be a finite point process with some sigma finite intensity measure m. And now we need the notion actually of a palm measure gamma x, which is defined here in terms of this disintegration equation. Okay, so then you have a palm process gamma x, and if gamma is a simple point process, then you can think of gamma x as the point process gamma conditioned on having an atom in X. Okay, if you have an atom in X, then it's natural to subtract the atom in X again, and this is what we call the reduced palm version of gamma x. Okay, and now we want to study Poisson approximation, and therefore we fix a finite Poisson process theta with another intensity measure L. And then we have the following theorem, which is from the paper of Bobrovsky, Schulte, and Yogeshwaran that I mentioned before, which says that the Kantorowicz-Rubinstein distance of gamma and theta is upper bounded by the total variation distance of the two intensity measures, M and L, plus an integral where we actually integrate the expected symmetric difference of gamma and its reduced Palm version. Okay, so there are a couple of things one can say about this theorem. So first of all, if gamma itself is a Poisson process, then, and this follows actually from the Mecke equation, then you can choose the Palm measure gamma x just as a process gamma plus delta x. So you can just add the point x. And if you then consider the reduced Palm version, then this is just gamma again. So in this case, the second contribution to the whole integral would just be 0. Right? So in that case, the theorem says that the Kantorowicz-Rubinstein distance of two Poisson processes is just upper bounded by the total variation distance of the intensity measures. That's the first thing. And the second thing, and this is actually the way we apply it, this is that we have here really a lot of freedom, right, in choosing the coupling of gamma and its reduced Palm version. So this will be the challenge in applying the theorem, because this theorem actually holds for all couplings of gamma and its reduced Palm version. And the difficulty in applications is really to come up with a good coupling. Okay, so how can we do this in our setting, so where we study the thinning of a Gibbs process? Okay, so how do we treat this symmetric difference? So let me introduce the notation Sx prime, which is just a set of all points W, or of all points Y and W, such that the balls Sx and Sy overlap. So you should think of this as the points Y that are close to X, right? And then I exploit the following bound. So the symmetric difference, or let's say the points in the symmetric difference, which fall into my observation window W, they can be upper bounded as follows. So first of all, you take here all points in gamma, which fall into Sx prime. Then you just add all points in the reduced Palm version in Sx prime. And then you only consider the symmetric difference in the complement of Sx prime. Okay? And now, actually only the last term will be the term to which we apply disagreement coupling. And here's now the important lemma. So the lemma says that the reduced Palm process Xi, and now this is a Palm process of Xi conditioned on having an atom X of the process gamma. So this is the Gibbs process Xi conditioned on the process gamma to have an atom in X. And the lemma says that this process is again a Gibbs process with an explicit Papangelo intensity, which looks as follows. So you just have your original Papangelo intensity kappa, you add the atom in X to your configuration, and then you have a certain weighting of, or with actually the thinning probability G. Okay, and the idea is now the following. If X is far enough away from Y, then you will not see the contribution of X in the Papangelo intensity. And you will also not see the contribution of y here in your thinning function. And both actually holds because of the localization of the Papangelo intensity and of the thinning function g. All right, so the idea is if x and y are far enough apart from each other, then the reduced Palm process will have the same distribution as the original Gibbs process. Okay? And I mean, this should now maybe remind you of disagreement coupling, because what we did in disagreement coupling was to construct the coupling of two Gibbs processes with the same Papangelo intensity, but with different boundary conditions. And the same thing we can do here now. So disagreement coupling on this set, so on this set W plus S without Rx, gives now a tuple of the process Xi and the reduced Palm process, such that each point in the symmetric difference is connected via the sum of the two processes to the boundary. Right? And then, and this was on a slide of Günter, so the sum of the two processes is actually stochastically dominated by a Poisson process, right? And if I now go back here to the picture, I mean, that's exactly what you see in the picture, right? So these paths here in the Poisson-Boolean model, they actually result from disagreement coupling. Right? So that's exactly what comes from disagreement coupling of the reduced Palm process and of the Gibbs process itself. So the idea is here basically that we think of the reduced Palm process as a Gibbs process with a different boundary condition, and this allows us then to use disagreement coupling. Okay, let me give you an example. And okay, so if I talk about examples, I could, or I would, in theory, of course, have to specify both the Gibbs process and the functional, but I will only specify the functional now and not give you an explicit example of Gibbs process, but there are, of course, many. Okay, so let's consider the observation window Qn, which is just a cube of volume n to the power of d in Rd. Fix some positive c and let un be the following threshold. You choose un as the largest u, such that the probability that there's no point of Xi in a ball centered at x with radius u is at least c over n. And then by continuity, the probability that you see no point in Xi in a ball centered at x with radius un of x will be exactly c over n. So you will have a thinning probability of c over n. And then we consider now the functional gamma n. And what we do here is actually that we consider all points in Xi for which there is no other point in a ball with a radius un of x around x. Okay? And then we rescale here such that in this observation window, the points are actually scaled to the unit cube. And then we have the following corollary. So, and this is now a small technical assumption. We assume that kappa of x and the empty configuration is equal to kappa of the origin and the empty configuration. So this is a little bit weaker of full translation variance of kappa. And let nu be a stationary Poisson process with this intensity C times kappa 0, 0. Then we have Poisson convergence in Kantorowicz-Rubinstein distance of this functional gamma n restricted to the cube Qn. So the idea here is the following, that so you will have a thinning with probability C over n, and in average you will see n times kappa 0, 0 points. And this is actually similar to the idea of the classical Poisson convergence theorem. So if you have just a binomial random variable, right, n with parameter Pn, and if n times Pn converges to a constant, then your binomial random variable will converge to a Poisson law. And that's exactly what we see here. The difference is, of course, that the different thinnings are not independent, right? But that's the way to think of it. Okay, so I mean, about the proof, so what we need to show, of course, is that the second moment contribution, that this vanishes asymptotically. So we basically have to find an upper bound for the empty space probability of a Gibbs process. And this relates to a very nice notion, and this is Poisson likeness of Gibbs processes. As far as I know, this dates back to a paper of Schreiber and Jukic about 10 years ago, but could even be older. So let psi be a Gibbs process which is stochastically dominated by a stationary Poisson process. We have this, right? Because we have a Papangelo intensity upper bounded by some alpha 0, and assume that there are constants CPL and RPL, right? Such that for all large enough R, all X and all configurations phi in the complement of the ball centered at X with radius R. So what we consider is a probability that the Gibbs process psi restricted to this ball around X with radius R is empty, conditioned on some arbitrary boundary condition, and then this probability decays actually exponentially in R to the power of D. And this, of course, explains why it's called Poisson likeness, because this is just the decay that you would expect from a Poisson process, right? And if we have this Poisson likeness, this allows us then, of course, to establish the convergence of the second moment contribution from the general theorem that I showed you. And there's actually a lemma which says that under a mild condition on the PI, we have Poisson likeness. So this is a very usual thing in our general setting. Okay, so let me use the rest of the time to talk about normal approximation. And again, we fix here an observation window Qn with volume n to the power of d, and we consider a non-negative functional on finite subsets of Rd. And then, so in the first place, we define actually a function Hn of some point process just by restricting the point process to the cube Qn. But more specifically, we can also choose Hn actually as a score sum with some score g, where g is now not just either 0 or 1, but can be any positive real number. Okay, and examples for this are the nearest neighbor graph. Right? So the nearest neighbor graph, or the total edge length in the nearest neighbor graph, I mean, this is an example which fits actually into the second description of Hn. So this can be really represented as a score sum, because you can somehow track the contributions of each point from the Gibbs process to the total edge length. And the second example is total edge length in the minimal spanning tree, right? Which is a little bit more involved example, and this is not so easily representable as a score sum. So this actually falls into the more general concept of a Gibbs functional. Okay, some literature again. So there is there's literature for normal approximation of Poisson functionals. And I think one of the starting points there was a seminal paper by Last, and Schulte from 2016, which developed the so-called Meyer-Walsh-Stein approach for normal approximation of Poisson functionals. And this was then later on refined by Last, Schulte, and Jukic for exponentially stabilizing functionals. And by now we actually really have plug-in bounds, right? Where you can just plug in your function and come up with nice rates of Poisson of normal approximation in Kolmogorov distance, for example. Specifically for Gibbs processes, there are two papers, one by Schreiber and Jukic, the other one by Jukic and Shah, where they study normal approximation for Gibbs processes, but they of course do not rely on disagreement coupling, but use a graphical construction of this Gibbs processes by birth and death chains, where they exploit then branching bounds. But so the drawback of this method is actually that it does not give you normal approximation up to the critical radius for Poisson Boolean percolation, right? So you cannot go that far with actually your Gibbs process. You are, in a sense, stuck really in the subcritical regime. So this is really the main advantage of our method here, that we can go all the way up to the percolation threshold. And then more general, so papers about normal approximation, and these are really classical papers, at least the first two by now, I would say. So Penrose and Jukic from 2001, this is the so-called martingale method. And a paper by Blashishin, Georgeshwaran, and Jukic was already mentioned by Günter, which considers normal approximation of general functionals. And then a more recent paper of Chen, Rollin, and Shah exploits Stein's method using Palm couplings. And so I would like to start now with this last paper and maybe briefly explain what they do and how we can exploit this and combine it with disagreement coupling. Okay, so Stein's method for normal approximation of point processes. So we consider a smooth approximation of the indicator W less or equal than U, and we set up the classical Stein equation, right? So that's how Stein equations look like. Okay, and now say that for some reason we have some function k of t, so which is a random function such that the expectation of h times f of h equals the expectation of the integral on the right-hand side for all random variables h with mean 0 and variance 1, and for all sufficiently smooth functions f. Okay, so what you can do then is the following. First of all, we want to study Kolmogorov distances. So we want to express the difference of the probability that some random variable h is less or equal than u and the probability that a normal random variable is less or equal than u. And this is approximately the difference of expectations of hu of h and hu of n. And then now, by definition of k of t, you can write this as a difference of two integrals, right? So let's start with the second integral here. So this just results actually from this second display here. And the first integral, I mean, what we use here is if we choose the function little f just to be the indicator function, then its derivative will be constantly 1, right? And because the variance of h is 1, this says that the expected integral of k of t is just 1, right? So this explains why we can put here the first integral. Okay, and now I'd like to explain to you how we can actually choose k of t. So say we have now this random measure here, right? So it's a random measure, not a point process anymore, because g can be any non-negative real number. We consider Palm versions psi of x defined on the same probability space, and we define now actually some functions h and hx, which is just a normalized version of the number of points of the cardinality of capital Xi, and we define delta x just to be the difference of hx and hy. Well, what can we do then? So we want to find now this function k of t in order to come up with a bound on normal approximation. So this can be written as follows. I mean, this is actually just the definition, what we use here, of the Palm process, right? So you can write this just here as a sum over all points in psi, and then apply the defining equation of the Palm process. Then you get this. Okay, then you can write the integrand as an integral from 0 to delta x, and you integrate over the derivative of f. And now you see actually how you can choose your function k of t, right? Because this you can write actually as an integrand where you take this ratio here times the difference of two indicators, where you consider actually the delta x, right? Which are just the differences of hx and h itself. So this allows you now to choose k in this way. And if I go now back one slide, then you see that if you can choose k, then this allows you to come up with an upper bound on the Kolmogorov distance, right? So the idea is really to choose k in this way. And now you can use disagreement coupling again to control the difference of h, x, and h, which were just defined in terms of the Palm process of Xi and the process Xi itself. Right, so here you can use then disagreement coupling again in order to control this difference. Okay, and this allowed us then to prove this theorem here. So we have two conditions. We have a moment condition, which is actually also very classical for central limit theorems. And here we need actually the sixth order of G to have a finite moment. And we have, of course, a stabilization condition. And yeah, so we need that the functional G is actually localized to a stopping set, right, where the radius of the stopping set has an exponentially decaying tail. And if we have this, then we can prove actually normal approximation in Kolmogorov distance of the functional Hn of Xi. Okay, so I would like to stop here, maybe, and yeah, invite you to look at the last slides, which consider normal approximation via the martingale method on your own, but I think it really makes sense to stop here, and yeah, I would really be happy to answer questions. Thank you.
Yeah, thank you, Moritz. A very nice talk. So yeah, we do have time for questions. So again, feel free to unmute yourself or raise the hand as you like. Or otherwise, I can maybe just start. Oh, well, Andre.
Thank you. Thanks. Basically, two short questions. Firstly, you mentioned naturally Stein method for the limiting theorems. Could you also use Malia-Weinstein? And also you used basically, I think that your construction is based on the Kantorovich-Rubinstein distance that you defined. Would a lot change if you would use any other different distance? Is this the best possibility, or could you use anything else here? Thanks.
Okay, first of all, thank you for your questions. Yeah, so the first question concerned the Meyer-Wurst-Stein approach. So the Meyer-Wurst-Stein approach uses Meyer-Wurst operators, right?
Sure.
Which consider certain at-one post operators. So the question is, how does the functional change if you choose one atom in X? How does this change your whole functional H or Xi? And I mean, this approach works very well for Poisson input. And for more general input, the way to think of this add-one cost operator is, at least in my view, actually not in adding just 1 point, but in considering a palm version, right? So the right way to generalize this is the question, how does the functional change if I add 1 point? So if I condition on having 1 point. So I think we need a more general concept here than this add-one cost operators. And I mean, your second question was on the Kantorovich-Rubinstein distance. And I mean, I think there's two things to say. So first of all, I think that the Kantorovich-Rubinstein distance is already a very strong distance, since it, for example, dominates the total variation distance. And but of course, you can think of what can change if we go to other distances. And for example, if you consider Wasserstein distances. So I briefly talked about this D2 distance. And I mean, there you have actually more general techniques which allow you, for example, to obtain Poisson approximation without constructing an explicit coupling of your process with this palm version. So this is what we are doing, what we have done with Nicolas Chenavier, right? So there we considered exponentially mixing beta processes, and in this generality, it is of course not possible to construct the coupling, right? So if you consider weaker distances and total variation, then it's often enough to not have an explicit coupling.
May I just add one additional thing? How extendable is your analysis in terms of function spaces, in terms of topologies and so on?
Yeah, it's very
you
much
analyze limiting theorems. This
yes.
seems a logical question, right? Thanks.
Yes, I think the theory works in high generality. I think most of it actually works on separable Hausdorff spaces, right? So I just think that, I mean, if you look at the literature on Gibbs processes, it very often works on RD, right? But I completely agree with you that from a mathematical viewpoint, a lot of this, if not all of this, can be done in high generality.
Okay, thanks. Thank you.
Any more questions? Maybe also just like a short one concerning like your last slide you presented. So as soon as you talk about approximation, one very natural question is how to quantify the error terms. So you put in like the log Q to the A. I guess any understanding what is kind of like the optimal, or to expect some of the optimal error terms, or any example
Okay, so
where
what
you
I
can
would
compute them?
expect that you do not need the log term, right?
Mhm.
So the optimal error term is expected to be 1 over square root of volume of Qn. So basically 1 over the square root of the size of your observation window. This is believed to be optimal. And
Okay, but is there an intuition why exactly this is capturing it?
Yeah, because your variance grows as Qn. That's basically
okay.
the idea. I mean, you can actually, okay, thank you for the question. This is a very nice thing. You can actually also use disagreement coupling for to prove actually variance lower bounds. And then we would be able to establish that the variance grows linearly in the volume of Qn. And then it's very natural to have actually 1 over square root of Qn. So I believe that the logarithm in our bound is actually just an artifact from the proof that you don't need it. Yeah, thank you.
Okay, all right. Any more questions, like for Moritz or Günter? Okay, it doesn't seem to be the case. So yeah, thanks to both of you. Really nice talks. And already as an announcement, in 2 weeks, we're going to have the next talks by, I think, Sissi Mayer and Daniel Ilchi, if I'm not mistaken. But there will be an announcement via email.
Thanks a lot.
Yeah, thanks everybody for coming.
Yeah, thanks for coming. Thanks for hosting us. Has been a pleasure.
Yeah.